Hello, my name is Philip. I'm a computer science PhD student at MIT, and today I'll be presenting our paper titled Thread Thinking Deeper with Recursive Spawning. We start with some background on the problem, which is that despite showing success in diverse settings, language models still struggle with tasks that involve long contexts, such as those that require extensive reasoning, retrieving information, or interacting with an environment. For example, we can test the ability of language models to reason over long horizon tasks in settings like ALFWorld, which is a virtual environment that allows a language model to execute tasks such as finding and cleaning dishes in a kitchen through a text-only interface. So here's an example task in ALFWorld. There's a description of the room and the goal specification, which is putting a clean plate on the countertop. Existing state-of-the-art methods such as React leverage a chain of thought-based reasoning framework, first reasoning about the steps that need to be performed to accomplish the task, then doing each step. This involves finding the plate, then picking up the plate, then cleaning the plate in the sink, and finally putting the plate on the countertop. The problem with these types of approaches is that when engaging in these long sequences of interaction with an environment, the model will often make a mistake, such as misinterpreting feedback from the environment, incorrectly specifying a command, or just losing track of where it is in the task like it does here. So requiring the language model to generate its response in a single line of generation is a significant limitation of existing frameworks. To address this limitation, we propose a new framework called Thread, which stands for Thinking Recursively and Dynamically. Thread frames model generation as an execution thread that, given a specific context, can run to completion or dynamically spawn new threads in a recursive fashion. When given a task such as interacting with a virtual environment like ALFWorld to put a clean plate on the countertop, instead of the language model performing the task in a single line of model generation, Thread enables the model to decompose the task into subtasks that are allocated to separate threads, which can in turn offload work by spawning their own threads. To illustrate Thread, we return to this previous example where model is tasked with putting a clean plate on the countertop in ALFWorld. The context for thread 0 is the task description. In this thread, the language model starts forming the response by stating that it first needs to find a plate. Now, instead of thread 0 doing the work to find a plate, it spawns a new thread by generating the special token. When a thread generates this token, the thread pauses and a new thread is created. In this case, thread 1 is created. The context for the original thread, thread 0, was the original task. Now, the context for the new thread, thread 1, is the last line of text generated by the parent thread, thread 0. Based on this last line of context, thread 1 can infer that its subtask is to find a plate. Thread 1 can then proceed with this task. In doing so, it can use the same special token to spawn its own child threads to offload work necessary for searching for a plate. Here we see that thread 1 spawns a new thread to check if there is a plate in the fridge. The new thread is thread 1.1. Thread 1.1 is then able to complete this task without spawning any new threads. And importantly, we see that all the complexities of opening the fridge and interpreting what is inside are compartmentalized within thread 1.1 and do not propagate to its parent thread. Instead, the parent thread only sees the task-relevant information returned by thread 1.1, which is that there is no plate in the fridge. To return this information, thread 1.1 uses the print statement shown here at the end of the thread. This information is returned to the parent thread. The parent thread can then continue with its task of searching for a plate. To do this, it will spawn a new thread to now check countertop 1. The feedback is returned the same way we saw with the previous child thread. And the process continues until a plate is found. It then returns the task relevant information to thread 0, which is that the plate 3 was found on countertop 2. Thread 0 can then proceed to spawn child threads to complete the remaining tasks of picking up the plate, cleaning the plate in the sink, and finally putting the plate on the countertop. Okay, so that was an example of how Thread can be used to accomplish long horizon tasks in a virtual environment like ALFWorld. But in the paper, we also show how thread can be used to enable LLMs to perform long horizon tasks involved in analyzing external data sources. For example, we see that thread can be used for answering questions about medical data from ICU patients. We test this using the Mimic3 database. This figure on the left shows an example of the clinical time series data provided by Mimic3 for ICU patients. Some examples of questions clinicians may want to ask about patient data are shown here. And if we take the first example, asking for the time of the largest increase in the shock index of a patient during their first 24 hours in the ICU, we can see how thread could be used to answer it in a manner similar to what we saw previously. Here, thread 0 spawns a child thread to create the table with the desired shock index values. This thread then spawns separate threads for retrieving the heart rate and systolic blood pressure, which are needed to calculate the patient shock index, which is the heart rate divided by the systolic blood pressure. It then proceeds to use the return data to calculate the shock index and returns the desired table to thread 0. Thread 0 then uses the data in the table to perform the analysis needed to answer the question. So we've seen two examples of thread. Here is a more general illustration. Overall, for a given task, it follows similar steps of spawning threads to complete subtasks. When a subtask is completed, the feedback is returned to the parent thread, which can then use the feedback to proceed with its task. We test thread in diverse settings involving long horizon tasks, including ALFWorld, which is the source for the first example we walked through. Thread significantly improves performance in ALFWorld for models of all sizes, ranging from GPT-4 and 3.5 to small Llama models. We also test on WebShop, which is a benchmark that tasks a model with purchasing specific items by interacting with the web shopping environment, as well as TextCraft, which is a benchmark that involves making Minecraft objects by interacting with the environment to find material and craft items according to the provided recipes. Thread again outperforms all existing methods across all models with both benchmarks. Finally, we test thread on benchmarks that involve answering questions about real-world trends with DataCommons and about medical data with Mimic3. We see significant improvements in the accuracy of the language model's answers to these types of questions with thread relative to the best existing frameworks, which require the model to complete the data retrieval and analysis in a single line of generation. In summary, we see that thread enables LLMs to perform tasks by recursively decomposing the task into progressively simpler subproblems that can be solved by separate child threads. And future work is focused on extending thread for multimodal reasoning in embodied environments.